Bismillahirrahmanirrahim. Good morning, everyone. Our today's lecture is about Gauss's law, and this is chapter number 23 of electricity and magnetism. To start with Gauss's law, we know we have studied chapter number 21 about static charges, chapter number 22 about electric fields, and today we are going to study the Gauss's law. Actually, Gauss's law provides us a very simple way to solve the complex geometry, seemingly complex problems of electricity and magnetism. As we have studied in physics that our primary goal of physics is to find simple ways of solving seemingly complex problems. One of the main tools of physics in attaining this goal is the use of symmetry. For example, in finding the electric field of the charge ring discussed in chapter 22. In chapter 22, we had discussed a charge ring. We calculated its electric field at a point P. And in chapter number 23, we are going to solve it in a different way. So for certain charge distribution involving symmetry, we can save far more work by using a law called Gauss's law, developed by German mathematician and physicist called Friedrich Gauss. He lived from 1777 to 1855. Gauss's law considers a hypothetical or imaginary closed surface enclosing the charge distribution. For example, here in this geometry, a Gaussian surface is a spherical surface, and you can see here a spherical Gaussian surface is supposed, and the charge resides inside that surface, in that closed surface. So first of all, we have to define the Gaussian surface. This is Gaussian surface, that is called, can have any shape, but the shape that minimizes our calculations of the electric field is one that mimics the symmetry of the charge distribution. For example, if the charge is spread uniformly over a sphere, we enclose the sphere with a spherical Gaussian surface, such as one in the fig, this one. Gauss's law relates the electric field at points on a closed Gaussian surface to the net charge enclosed by that surface. So we found that Gauss's law actually relates the electric field at points on a closed surface, at any point on the closed surface, and to the total charge enclosed by that surface. Okay, so from here we can define mathematically that Gauss's law is 1 over epsilon naught times the total charge enclosed by that surface. Okay, so we come to this definition later. Before that, we need to have concept that how a field behaves, okay, how electric lines of force behave, and how a vector field behaves to the surface or cross-sectional area of a plane. So suppose that, as in the figure down over here, we have a uniform velocity v at a small square loop of area A. Let phi represent the volume rate, flow rate per unit time at which air flows through the loop. This rate depends on the angle between this V and the surface area A, that is V dot A, VA cos of theta. So phi is equal to VA cos of theta. A is constant, so we take it outside this parenthesis. So V cos of theta component in the direction of area vector A. So you can see when V and A are perpendicular, the value will be maximum. When there is angle, the value decreases by cos of theta, and when it is perpendicular, the value will become 0. Okay. So what is flux? The word flux comes from the Latin word meaning to flow. That meaning makes sense if we talk about the flow of air volume through the loop. So we always consider the example of air volume flowing through a room, okay, that how much air is flowing through the room and what is the angle of the flow. So these are two main components. Flux no longer means the actual flow of something through one area, rather it means the product of an area, which was V cos of theta, in the direction of area unit vector and the field across that area. So this is the definition of flux. Here in this example, we have considered different patches 1, 2, and 3. You see, and this is the lines of electric field flowing in this direction over this surface. So at point 1, this is the direction. At point 2, we have this kind of direction, value is 0, this is less than 0 because angle is greater than 90, cos 90 greater than 90 is negative, and for this area the value will be positive, phi is greater than 0. Delta A and E have angle theta. So from here we can define phi is equal to summation E dot delta A. We break the surface into small patches, small mesh. We break it into mesh with a very small unit size. So we add the flux from every small patch, and then finally we add it up using mathematical technique, that is integration. So phi is equal to loop integral, means closed integral E dot dA. So we integrate it over all the closed surface and we calculate the value of the flux. Newton meter square per coulomb is the unit of flux. And another definition of the Gauss's law is epsilon naught phi is equal to Q enclosed, or we can say the flux in a closed surface is 1 over epsilon naught times the total charge Q enclosed by that surface. So phi is equal to Q enclosed over epsilon naught, or epsilon naught phi is equal to Q enclosed. So you can define it both ways. And by substituting the values, we find the value of phi from previous, this value, if we put in this equation, we have epsilon naught loop integral E dot dA equal to Q enclosed. So here are different geometries. You guys have to apply the same concept on this geometry and find what would be the value on different surfaces. So first of all, we can derive Coulomb's law from Gauss's law. So Gauss's law is more general form compared to the Coulomb's law. So from Gauss's law, epsilon naught loop integral closed integral E dot dA is equal to epsilon naught phi. So epsilon naught phi is basically equal to epsilon naught come over here, and Q enclosed, which is equal to total charge enclosed by that surface. So epsilon naught E loop integral dA equals Q, if Q enclosed is total charge Q. So, and total area, surface area for a sphere is 4 pi r square, epsilon naught E 4 pi r square equals Q. And from here we can calculate the value of E. E is equal to 1 over 4 pi epsilon naught Q over r square, because 4 pi r square is E in epsilon naught into 4 pi r square. When it goes to the other side of the equation, it becomes in the denominator. It comes down in the denominator. Similarly, you can calculate the physics of different shapes, charge distribution on different shapes. You can go through this. Another example is the very important example, external electric field. This is for a glass, this is imaginary surface, like a cylinder-like surface. For a sheet of charges, you can calculate the electric flux through this surface. Phi is equal to E cos of theta. E is equal to 2 pi r h, because the flux is to the end of the surfaces, to the both end of the surfaces. So it will be 2 pi r h cos of 0 E into 2 pi r h. Epsilon naught phi is equal to Q enclosed. Epsilon naught E 2 pi r h equals lambda h. E is equal to lambda over 2 pi epsilon naught r. The same way you can calculate for planar symmetry and two conducting plates as well. It will be twice if they have the same. If they have opposite charges, it becomes twice. And then we have different sphere, S1 and S2, and small r is the radius for the larger, and capital R is the distance of the charge distribution. So we consider these different geometries, and we find out that the charge enclosed by sphere of radius small r over volume enclosed by sphere of radius small r is equal to the full charge over full volume. So the ratio remains the same. So we put value Q prime over 4 by 3, which is for sphere, 4 by 3 pi r cube, volume for sphere, and Q prime is the charge enclosed by that sphere, equal to Q over 4 by 3 pi r cube. Yeah, means total charge enclosed by the full charge enclosed by the full volume of the sphere. So here, from here you can calculate Q prime equal to Q into r cube over capital R cube. So Q prime is equal to Q, and q over 4 pi epsilon naught. If you move this value to the other side, if we substitute this equation into 23.17, so 23.17 equation is this one. We put value of q prime and we get E is equal to q over 4 pi epsilon naught r cube into r. So this calculate the charge for different spherical surfaces, electric field for different spherical surfaces. Thank you very much. Assalamu alaikum, and we'll see you in the next lecture.